a water planet. Approximately 70% of the Earth's surface is covered with water. Of all the water in the world, more than 97% is salt water found in the oceans. Of the remaining 3%, 2/3 is frozen in the polar ice caps, leaving approximately 1% of the world's water as available fresh water. We know that without safe, clean water, society as we know it would not function. Protecting and preserving this vital natural resource is a national priority. This production is the second in a series in regard to nitrogen in wastewater. If you have not already done so, you should view the first video in this series. The first video deals with the conversion of toxic ammonia nitrogen into non-toxic nitrate. This video will focus on the removal of total nitrogen, or more specifically, de-nitrification. While nitrate is not toxic, it is a nutrient and can act as a fertilizer. Phosphorus is also a nutrient that acts as a fertilizer. So what is the big deal with nutrients? Nutrients in excess can cause a deterioration in water quality. In fact, one of our national treasures, the Chesapeake Bay, is threatened by nutrients. Excess amounts of nutrients cause rapid growth of phytoplankton, creating dense populations or blooms. These blooms become so dense that they reduce the amount of sunlight available to submerged aquatic vegetation, or SAV. Without sufficient light, plants cannot photosynthesize and produce the food they need to survive. The loss of sunlight can kill the grasses. Algae may also grow directly on the surface of SAV. Unconsumed algae will ultimately sink and be decomposed by bacteria in a process that depletes bottom waters of oxygen. Like humans, most aquatic species require oxygen. When oxygen in deep water is depleted, fish and other species will die unless they move to other areas of suitable habitat. Additionally, nitrates in drinking water supplies can cause problems as well. In drinking water, nitrate has been linked to a fatal blood disorder in infants known as blue baby syndrome. As you can see, reducing nutrients in waterways is an important factor in maintaining water quality. Many treatment plants in Pennsylvania will be noticing limits for nutrients in their facility NPDES permits, especially those in the Chesapeake Bay watershed area. This production will focus on reducing total nitrogen by utilizing a process known as de-nitrification. In its simplest terms, de-nitrification is a biological process of converting nitrate into nitrogen gas under anoxic conditions. In order to achieve denitrification, you must have a good nitrification process. Typically, organisms associated with denitrification are less sensitive than those used for nitrification. It should be noted that, as with nitrification, not all treatment plants perform equally when it comes to denitrification. When comparing basic processes, the activated sludge process typically works better at achieving denitrification when compared to lagoons or fixed film reactors. For fixed film facilities, a denitrification filter may be added to the end of the biological process to achieve denitrification. Typically, a methanol feed would be needed to provide a carbon source ahead of the denitrification filter. Since lagoon systems struggle to nitrify in the first place, denitrification would be very difficult to achieve without significant modification. In terms of activated sludge, extended aeration and sequential batch reactors can work well for achieving nitrification and denitrification when properly configured. As for the least capable activated sludge facility for denitrification, the contact stabilization process may be the most limited in this respect. There are a number of different designs to achieve de-nitrification. A review by your facility engineer will be necessary before retrofitting any system to achieve de-nitrification. There are a number of advantages to the de-nitrification process. In fact, any activated sludge facility that must nitrify should also consider de-nitrification as well. The advantages are energy savings, reduced chemical costs, better process control, reduced sludge production, and better effluent quality. Let's take a closer look at each of these advantages. Energy savings is achieved through reduced aeration costs via the uptake of nitrate in the anoxic zone. In fact, 60% of the oxygen requirements for nitrification are returned through de-nitrification. Of the 4.6 pounds of oxygen required for nitrification, 2.86 pounds are returned through the de-nitrification process. As you may recall, aeration costs can actually double in facilities that must nitrify, so a 60% reduction can add up to significant savings. Reduction in chemical costs. As you may recall, approximately 7.2 pounds of alkalinity is consumed in the nitrification process. The process of de-nitrification returns 3.6 pounds of alkalinity to the system. This will reduce the amount of alkalinity that may need to be added in alkaline-deficient systems. Better process control. Typically, the anoxic zone helps to control troublesome filamentous organisms and provides for better sludge settling characteristics. The uptake of CBOD in the anoxic zone starves the troublesome filamentous organisms of their food source. Reduction in sludge production. Studies have indicated that overall sludge production drops by 5% in facilities that de-nitrify. By today's standards, sludge handling and disposal is a significant cost for most facilities. Better effluent quality. By reducing total nitrogen, the quality of the effluent is improved, making for a better water environment. In order to reap the benefits listed previously, the anoxic zone must come first. As you can see, there are some real benefits from utilizing de-nitrification that can reduce costs, make for better operation, and produce better water quality. So how do we achieve de-nitrification? In activated sludge, this is typically done through an upfront anoxic zone with a nitrate recycle flow from the end of the aerobic zone. As a rule of thumb, about 1/3 of the tankage is used for anoxic treatment. In a batch reactor, the process will take place during an anoxic period, where there is mixing without aeration. In fixed film installations, you may find a denitrification filter being used. In cases where total nitrogen limits are quite low, you may see multiple anoxic zones. In the anoxic zone, heterotrophic facultative organisms search for another electron acceptor when elemental oxygen is depleted. In this case, the organisms will use nitrate. The nitrate is obtained by a recycle flow from the end of the aerobic zone. In the anoxic zone, there is a significant uptake of CBOD. The uptake of CBOD tends to starve filamentous organisms of their food source and allows for the growth of nitrifying organisms in the aerobic zone. There are a number of factors and parameters that impact the process of denitrification. They include efficiency of upstream treatment units, carbon, dissolved oxygen, mixing, nitrates, temperature, toxic material, facility design, and wet weather. Now let's take a closer look at each of these factors. Efficiency of upstream treatment units. From the time wastewater is generated through the collection system and through all of the treatment processes in a treatment plant, the process of denitrification can be impacted by anything that happens upstream. For example, certain substances that could be accidentally or intentionally dumped into your system could cause the loss of biological organisms. The development and enforcement of sewer use ordinances can reduce the likelihood of unwanted substances entering your system. After the wastewater is generated, it then goes into the collection system for conveyance to the treatment plant. In the collection system, if excess water enters the system, it can cause a washout of biological processes in the treatment plant. After the wastewater arrives at the treatment plant, the operator must monitor all treatment processes. To maintain nitrification as well as denitrification, the treatment system operator must be vigilant and take actions to prevent or stop malfunctions and undesirable events throughout the entire treatment system. If you lose nitrification, the denitrification process will fail as well. Carbon. The heterotrophic organisms need a carbon source. Typically, this is supplied in the raw wastewater as CBOD. In cases of multiple anoxic zones, or where there is insufficient carbon, a supplemental carbon source such as methanol may be used. Dissolved oxygen. In the anoxic zone, we want to deplete all of the dissolved oxygen. In fact, the presence of DO inhibits the denitrification process. We typically want to see DO levels close to zero, and certainly less than 0.3 milligrams per liter. As you can see from this chart, the presence of dissolved oxygen dramatically impacts the specific growth rate of denitrifying organisms. Mixing. There needs to be adequate mixing to maintain a homogeneous mixture in the anoxic zone. This is typically achieved with a submerged mixer. Nitrates. The facultative organisms need nitrate for respiration. This is typically achieved through a nitrate recycle brought back from the end of the aerobic zone. The rate of denitrification is controlled in part by the amount of nitrate recirculated from the aerobic zone. As you can see from this chart, your nitrate recycle should be at least 200% of the influent flow. Temperature. As with nitrification, denitrification rates slow down during colder weather. Toxic materials. Typically, the denitrifying organisms are less sensitive to toxics when compared to nitrifying organisms. So if you are able to maintain good nitrification, denitrification should not be a problem. A good sewer use ordinance that, when properly enforced, restricts the introduction of toxic or dangerous materials into a system is a must. Facility design. You must have adequate tankage to achieve both nitrification and denitrification. Be sure to review your requirements with your facility engineers before you begin to retrofit. Wet weather. Many treatment systems are severely impacted by wet weather events. Maintaining the anoxic zone may be difficult during times of very high flows. So now let's briefly review what takes place during single-stage denitrification in an activated sludge facility. After preliminary and primary treatment, the raw wastewater enters the anoxic zone, where oxygen is depleted and the contents are mixed. Nitrates are added to the anoxic zone through a recycle from the end of the aerobic zone. The facultative organisms utilize the nitrate for respiration and convert the nitrate into nitrogen gas. In the anoxic zone, carbonaceous BOD is significantly reduced. After anoxic treatment, the wastewater flows into the aerobic zone where nitrification takes place. After the aerobic zone, the wastewater is clarified, with the return activated sludge going back into the anoxic zone. The clarified water then goes on for disinfection, or it may go into another biological stage if total nitrogen limits are quite low. System operators need to maintain all of the factors that impact de-nitrification. Process control testing and good record keeping are a must. The use of an oxidation reduction potential probe can be quite useful in determining the effectiveness of your treatment process. As with any biological treatment process, proper monitoring and process control of upstream treatment units is a must. If there is a failure in the de-nitrification process, partial de-nitrification could take place and lead to the production of nitrite. Nitrite can cause the demand for chlorine to increase dramatically. In addition to removing total nitrogen, many facilities will have total phosphorus limits as well. Phosphorus can be removed biologically or through chemical precipitation. For biological removal, this is typically accomplished with an upfront anaerobic zone. Chemically, the use of alum can precipitate the phosphorus. Other coagulants may be used as well. Nutrients, a fundamental requirement for life. Too many nutrients and life can be threatened. Through the proper operation and maintenance of wastewater treatment systems, under the watchful eye of skilled operators, our water environment is protected and maintained, making our water planet a better place for generations to come.